I'm going to go through here, I'm going to have a bit of a recap to start with, going through how we came about doing this, and some of the slides that I put up last year. Did anybody see me? Not here last year, but in Chicago last year. There's one nodding head and a hand, so it's two of you, so apologies for that. What I'm going to do, I want to sort of go through a little bit of that and show you what we set out to do about 18 months, 2 years ago. What I came to SpringOne last year in Chicago to sort of show what we were working on with a single client at the time. We had some ideas for some others. We've now got, it's approaching a dozen clients. And when I talk about clients, these are all large major banks. If you take at least 80% of those are in the top 10 tier, top 10 banks on this side. So these are big clients. I go out of my way not to mention the names of these clients for fairly obvious reasons. For those that, I suppose it's not always that obvious, but if you imagine you're working in you have a large bank, the bank is worth umpteen $100 billion in terms of market cap. The same is true for a large company like Apple or any of these large companies. If they were to say that they were using a particular type of technology, and that technology were to suddenly be found to have a flaw in it, the flaw may be some quick way of getting through the system, or some flaw in the encryption mechanism used, or something, potentially the valuation of that company could lose anything as small as 1%, for example. If you've got a market cap of $100 billion, that's $1 billion wiped off your company. And that's the main reason why you'll find that large banks, large organizations do not promote the software that they're using. They don't necessarily even go as far as saying that even the large companies, the banks will not say they're using Oracle or Sybase. It tends to be fairly general knowledge, but you won't find references for Spring integration, for Mule, for Oracle liquid data, for any of these things in any of these large organizations. And for that reason I have to be very careful about the names that I put on these, and I've had to obfuscate some of them a little bit for those reasons. But I'm more than happy to, since there's no cameras in here, more than happy to go into a little bit more detail in some of these things. So about a year ago, we've been working with, my company had been working with the VMware Spring Integration, or Spring guys, for some time, and we have a lot of mutual clients. Obviously our clients are all the financial services side, and we've been working on these mutual clients for a long time, and it suddenly appeared to us that there was quite a niche that we could sort of join these two technologies, or two technologies that we had together, and produce something that would make it much easier for the client. And obviously with a company like Spring having fairly recently been acquired by VMware at the time, of course they're trying to get into financial services. They're already in, but they're trying to make money out of financial services, so it appears to be a very large carrot, and there's a lot of drive behind that. So, as I say, a year ago we were talking about a client, and a client was using this. That client has got into production, and we have now several large clients that are using this. So what's so special about the integration? Why is it such a big problem? So there's 2 points I want to give you here. I want to show you the complexity of the environment that we work in. I'm sure it's you have equally complex systems, but I would put a challenge, probably best solved over in the bar, that these systems are probably verging on the most complex systems you can possibly imagine, just purely because of the fact that they have to function. There are a few other things, obviously, in Medicare and things where things have to function, but for the entire bank as a whole to function, to exist, to compete with the others, all of these integration things have to work. So let me show you a typical physical deployment diagram. And this is just a small part of it. Now, if you walk into any large bank, in the, as I say, I don't mean the retail part of the bank, so if you walk into your bank where you cash your checks and things, but if you go into the, obviously the Bank of Americas, the JP Morgan Chases, the Cities, to name a few in this country, if you walk into those large corporate offices, you will find these up on the walls in the corridor. You'll find them in people's offices. You'll find numerous different color codings on them. Some of them are color coded depending on risk. Some of them are color coded depending on the resources, the assets, and the various other bits and pieces. So every individual color codes these in a different way. Some of them have big lines and marks around them, and of course they print out these things regularly. But that's to give you some idea. And the bits around the edge of the green are effectively just the different lines of business. So if we look at this in a slightly different way, this is the functional architecture. And so if you walk in again in these things, you're going to be asked, can we see the functional architecture, the physical architecture, the various different parts. This is basically taking all of the different functions within the bank and looking at what those functions provide. So I'm assuming your eyesight is, apart from those at the front, let me just read out a few of these. You'll recognize them obviously: sales, trading, client relationship management, trade desk support, funding, payments, tax, fell control, margin, billing, all these sorts of bits and pieces. So if we take out a few of these, we start to get down to the integration layer. So if we start from the top, I've arranged these from the top downwards. The top is the trading, so this is where they're sitting on the trading floor. They're listening to price feeds. They're deciding they want to trade. So hundreds of thousands of messages a second coming in there with different prices. They decide they want to actually execute on some of those trades. Sometimes it's done automatically, sometimes it's done manually. Sometimes the manual triggers off automatic, and sometimes the other way around. So as these go down, they need to go into risk control. Can we actually do that trade? Should we do that trade? What is the risk, not just on that trade, but all of the other trades that it affects on those? Those feed back into the system to decide whether that trade can be executed or not. And of course this all goes down into pricing, and then position management, limit keeping, and all these sorts of things to find out whether you have too much exposure to a particular counterparty or third party. So as these work their way down, eventually you're now down maybe a day away from where you made the trade. And of course these trades have to be settled. So they have what's called netting, where they'll work out how many trades were made to a particular organization. All of those things will be added up, and they'll effectively say this amount of money going in, this minus this amount of money going out, this is how much we need to pay. And then we get down into settlements and various other bits as we go down the slides. So as we work our way through this system, each and every single one of these has integration typically with 2, 3, 4 plus other machines. And each one of those, as they go down, uses quite typically a different mechanism to integrate with. So it'll give you some idea now why we had that complexity before. So we're starting in the top. Typically we're in what we call low latency, high frequency. So we can't use XML. It's got too many silly brackets on it. We need to be down into something very efficient. It's not always encrypted because encryption itself slows things down. So it's very, very efficient mechanisms. It's basically diffs on the previous message. So a message comes out and we send over the differences between the previous ones, a bit like a sort of a JPEG encoding, for example. As we go further down, we get into some systems which haven't changed maybe for 20 years, and those will be sending comma delimited files. They were invented or designed prior to XML. And then we'll find some other systems that need to communicate with other banks. And then there's been sort of a process through that to mature it, and of course you'll start to see some standards. So we'll start to find XML appearing in certain bits, and eventually down into the bottom where we send the payments, we're into something like Swift, which again has been around for 30 plus years. So internally in the bank you'll find a whole different plethora of standards, and externally we'll find a whole different style of standards as well. Working their way down from high frequency in anything from tens of thousands, hundreds of thousands per second, down to the trades where we'll get a few per second, down to, in the accounting, we're down into the few per second, maybe every few seconds, and then finally into payments. Even the largest banks, the very largest user of Swift, for example, is Citi. On the Swift network, they put 2 million Swift net messages a day. So it's not a massive amount, so it's relatively easy to handle. So going back to that again, you might think, okay, that's not too bad, but now in comes the complexity of the fact that this is now global. So we thought about this just for one bank, but every single one of the banks, the large banks, has a global representation. We're completely global these days. So you take Citi, JP Morgan Chase, HSBC, for example, They have representation here in the US, in Europe, Asia Pacific, and obviously in numerous other places. They don't tend to have the investment banking part in these other places like the places that are not on there. They tend to be sort of subsidiaries. So you'll find Asia Pac will be out of Hong Kong, Singapore, for example. Europe typically out of London, and obviously the US is typically out of New York. So I mentioned some of the external ones. If you look at the externals, we've got regulatory bodies. We've got, so each of those traces that I went through on the previous slide, from the trade made at the top or right the way down through the payments, there are now new regulations that insist that we must be able to demonstrate that we made the best choices for our client. So not only do we need to store the execution of that trade as it goes through that system, all the way down every single part of that, but also all of the things that were decisions that were made in the process. So all of the prices that came before we actually made that, to prove that the decision we made was the best one at that time. So there's an awful lot of storage of these messages. There's an awful lot of processing that goes through it. And obviously, once you go back through that, you're going to want to do back testing, you're going to do what-if scenarios, and you're going to want to see your positions and exposure. And there's increasing push now, because the banks have screwed up so much, not just entirely their fault, the fault of different pricing risk bodies and various other things, but we basically need to keep an awful lot of information. So that gives you some idea of the complexity of this. We can take something as simple as a comma delimited file. This is probably still a significant proportion of the messages going in and out of the bank, the messages that are going from one system to another within the bank. It's surprising how many of these comma delimited files you come across. One service provided by a lot of banks is called prime brokerage. So there are smaller banks, hedge funds, etc., that don't have all of this back office processing. They're typically, hedge funds are typically traders who have a nice big client list. They go off, take some of their clients with them, and they create a hedge fund. That hedge fund turns over ridiculously large amounts of money. I mean, in the tens of billions, hundreds of billions, and they have portfolios and those sorts of numbers. The amount of money they make out of these is in the tens or hundreds of millions. There were 3 guys who left JP Morgan Chase a number of years ago. Their biggest problem was, do they pay, how to get rid of their money. They each paid themselves $100 million bonus in the first year. So if you think you're making good money in IT, think again. But that's just 3 guys, and there's not many of those 3 guys. There's an awful lot of us guys in the IT business. But so coming back to these comma delimited files, so why did I mention prime brokerage? One of the main things that these hedge funds do is to send their trade data to be processed by the banks. So they're busy working on, they effectively do the top layer of that big pile of functional programming, the functional architecture that I showed you. They're effectively doing the top part, and they then send all of the trades that they've done that day or that hour over to a large bank, and that bank does the processing for them. And typically they arrive in, obviously not that actual format, that's just an example file, but they arrive in a large comma delimited file. This comma delimited file could be hundreds of thousands of rows in size, but you can imagine the importance of being able to process that, and what happens if you make mistakes. You make one small mistake on some of these numbers. These numbers are billions of dollars. Billions going in, billions going out. The net result of that may only be a few tens of thousands of dollars profit. But if you put some money in one place, you get some interest on it, and you send it back out again, that's a billion in, billion out, $20,000 profit in one day. That's how the hedge funds make the money. But if you make one mistake on a decimal point on these things, or you process the date wrongly, because you Americans, who's not American here? So I just know who I'm not insulting here. Thank you. Yeah, and anybody who's sort of first generation, you can consider yourselves non-American. That's good. You Americans seem to have this strange way of putting your dates the wrong way around. And I always find it amusing when the Americans refer to it as the European style. It's not European, it's the rest of the world. But you can imagine if you put these dates the wrong way round, as you do here, you'll get something like 10-8. So 10-8 in this country means the 8th of October, whereas for us, for the rest of the world, it's the 10th of August. So you can imagine that you get these things the wrong way around and you're paying interest on the difference of dates or something like that. The amounts of money are just absurd. So it's absolutely vital that you process these correctly. I'm going to get to how we do that soon. And it's vital that these are validated. And this is what I'm going to cover, and this is why we're using these, what we're going to be using. What I want to do is to sort of show you why it's so important that we do this. It's not just something that we pick up. If it goes wrong, that's fine, we can throw it away. A fixed message. Now, this is not necessarily the messages that come directly off the price feeds. The price feeds tend to be in amusing formats called itch, ouch, and things like that that come off the Chicago Mercantile Exchange, the Intercontinental Exchange, New York Stock Exchange, etc. But as we go down, the trades themselves, which are much lower down, we're in the hundreds per second, maybe thousands, low thousands per second. These are all the trades that are executed on the exchange. They come in this format called fix. Fix is, there is a high performance version of this called fast, which is again the diff. But this, the basic format is fix. We're now on fix standard 5.0 SP2. But this is an example 4.4, which is still the most commonly used one. Effectively, it's tag value pairs. Now, those spaces that you see there, so if we read across, 8 equals fix 4.4, that's obviously the standard, 9 equals 1, 35 equals AK, 49, obviously, it's obfuscated, so we just put strings. In between each of those is a control A character, so 0, 1 in hex. Now, if you're parsing that, any one of you here that's even got the most basic programming skills would think, that's great, I'll just tokenize it and bung in some, put in the 0, 1 character, and I can tokenize it and I can get all the information back. Yes, you sort of can, but you'll very quickly become extremely stuck because you'll realize that some of those are repeating fields. So if you start to create yourself a little hash map of them, you'll start overwriting the hash map with the recurring values as they come down. And in some of those sections, you can't see it visually here, but there are different sections. Well, if we're doing a trade swapping two different currencies, we'll have leg 1, leg 2, and they'll obviously have the same repeating fields in them about who's paying what and how much and what currencies. So it gets a little bit more complicated. You've actually got to create a structure behind this to be able to store it. So already we're off the sort of nice simple stuff onto the sort of starting to get a bit more complicated. Go down into Swift. This is where it starts to get really nasty. Now this is tag value pairs. I'm sure you can recognize the tag, 16R, 20C, 20C, 23G. Everybody recognizes those. They're favorite tags. Been around 30 years. I'm sure you all know them off by heart by now. You can see the header, what we call block 1, 2, and 3. 3 is just towards the end here. This is just the header of the message. We can get quite a bit of information out of this. We can see, for example, in block 3, right at the end, it's an MT564, which is a corporate action. This message is quite a bit longer than this. They're not huge, but it's quite a bit longer. This is the message which is sent for the payment. So if ever any of you here have made a payment, not by credit card, but to send money to a bank, perhaps when you've gone on vacation outside of the US, for example, or when you're going on vacation into Europe and you need to pay for something that doesn't take credit cards, and there's plenty of those occasions, you probably need to send a SWIFT payment. So you'll have to walk into the bank and fill out this form that fills out a lot of those details. Somebody will then manually write that down, key it in, and someone will probably print that out, hand it to someone else who will then manually key it again. Unfortunately, that's the way a lot of banks still work, which gives us all a great opportunity to sell them Spring integration and some nice tools around it. So we can see some information hidden in here. In the red there, I've put out the Federal Reserve, New York, in the US. It would obviously be one of either the source or the destination. And then we can see the date here, 2012. It is in normal format. So the same as, by the way, when you come into the US, you have to fill out your immigration forms in normal format. So it's year, month, day, or day, month, year. And the time on that. So as these go through, what we need to be able to do to be able to route this, to be able to process it, to do anything with it, we have to know the information in this. It's all very well taking the message, being able to tokenize it into tag value pairs. We need to be able to get the information out, because if we want to route this, to prioritize it, if we want to prioritize this by value, by date, by to put them into blocks or segments, based on who we're paying, how much we're paying, what date we're paying, we need to be able to extract this information out. Getting on to the last couple here. FPML, this is one of the new delightful standards, financial products markup language. It's actually in XML, and if you're ever designing a new XML standards and you want something which is, you want an example that is well designed, I would highly recommend you take a look at this. isda.org or isda.org. It's a very, very good example of how to design XML. It's got numerous standards. I think we're on about 50 to 60 different versions of it now. No one bank uses any one of those. They take one of the versions or bits of several of the versions and they take the bits out of it that they want and they then customize it yet again. So we've got all of those to manage as well. And then we get onto things like ISO 20022, which doesn't actually define any messages themselves. It defines a metadata around which you can form messages from. So one of those is SEPA, which is the Single European Payments Area. You might think that's irrelevant. Maybe in a year's time it is totally irrelevant. But for the moment the euro is still there. And some of the biggest customers using this standard are not obviously, but are in fact the American banks, because any bank from any country in the world that wants to work with the euro or the eurozone has to conform to some of these standards. Now the European banks themselves haven't yet completely conformed to these, so it adds to the continuing ongoing confusion, and now obviously with Greece and Spain, etc., messing around with debt, and there's going to be some doubts left in whether they should be making this merge. But this is important for the US banks. And what's interesting here is that, again, there's no message formats actually defined. Finally, on this side of things, this is just all I wanted to cover from the complexity on the both sides. We have rules. Now, I mentioned the dates before. It's sort of funny, but it does actually cause quite a lot of issues. There are other things. For example, on the continent. When I say continents, as a Brit, I'm referring to European continent. We tend to be conveniently located halfway between the US and Europe, as in the United Kingdom. But the continentals, they use commas for their full stops and full stops for their commas. I don't mean in text, but in numbers. So if we want to say 100.00, they use 100.00. So it's little things like this that if they get confused or go the wrong way around and add to that the dates, that things get a little bit difficult. Now, you might think that's a nice syntactic rule, but if some of those things get through those rules, for example, the dates are a good example, we need new rules that, in addition to semantic rules, that protect the actual messages themselves. So on the dates, we can have the date must be within, or it must be today, for example, or the date must be within, it must be greater than another date, or there must be at least 3 working days between these dates. Some of these are horrendously complicated, and these rules are mandated. If you use these standards, whether they be Swift, FPML, FIX, etc., or SEPA, ISO 20022, you have to follow these rules. So you've gone off and you've coded your little FIX decoder. You've used your tag value pairs. You've thought about how you're going to do it in a hash map, and you've branched off all the bits and pieces. You've decoded it. And now all of a sudden somebody comes up with a list of 150 of these rules, which you now have to implement. Now if you've coded this using tag value pairs and a hash map or something like that, you've got to refer to each one of these. You've got to go and look it up in the standard to work out which one of those it applies to. And you've got to encode this rule in some mechanism that allows you to put it into the message. And believe me, that's a headache. It's a lot of work putting these in. It's true to say, however, that not everybody actually runs these rules. It's a bit like saying if you have valid XML, you must validate it against the schema. As I'm sure all of you know, not everybody validates against the schema. And you have some rather weird results happening when something slips through. There was a client recently who was taking messages off the Chicago Mercantile Exchange, and you'd imagine they sort of should really know what they're doing. And the messages, if the message didn't have it had a timestamp, so it was a date and timestamp. If they didn't know the time, they would put 99.99 in the time. Now, if you're validating that against a schema, the Microsoft thing apparently passed it through, fine. But if you do it on Xerxes, it said, hang on, you can't possibly have 99 hours. And so, of course, it threw out an exception. And of course, you can't not accept these deals because they come from the Chicago Mercantile Exchange. You've got to deal with them. So you find yourselves having to make some sort of weird exception cases. So yes, there are rules. Most people comply to them, but there are some sort of weirdities on top of that as well. So ultimately, we want to get to the business. I'm assuming most of you here, who's programmers, architects? Put your hands up if you're programmers and architects. Or is there any just pure management, never touch the code stuff here? Ha ha ha! We can insult them now. So your managers, those nasty people, who pay you lots of money, of course. Sorry? Ah, there you go, yes. So somebody must be to blame for the US date formats. The managers, you're telling them exactly what I've just told you. It's bloody complicated. You've got these really nasty messages and you've got all these bits and pieces, and then our clients are not sending us correct data, then we've got to validate them, got to put all this stuff in, and they're just basically saying, but you told me when we got this ESB that we've just spent $20 million on, that it's all going to be nice and simple. All we need to do is put lots of boxes and draw lines across to them. And you well know it's not quite that simple, but that's what they're expecting. So what we try to achieve is some happy balance between that. The flow on the bottom is not particularly important, but it's just to give you an idea of what they're expecting. Messages in on the left-hand side, processed messages on the right-hand side. And in between, we do a little bit of jiggery-pokery. We enrich the messages, we test the messages, we send the rejects off somewhere else, we trigger alarms if something's not working, we get some people involved to rekey stuff, we put them in the database, and there's some other little bits that add on to the top, and we can do some analysis, and we get it all out the other end, and out the other end everything's nice. So the business guy's sort of gone off and got one of his architects, one of these people that sit up in the ivory tower that's not a hands-on architect, and he's drawn this nice thing using the enterprise integration patterns, and just hands it down to the coders, and here you go guys, beautiful spec, nothing to worry about now. Into your nice waterfall method, you've got to go and you've got the next 6 months to go and code this. And of course they don't like anything other than waterfall because it puts too many questions back on the people who are writing all the paperwork. And of course they don't know the answers, so of course an iterative agile mechanism doesn't work. So what are the drivers for what we did? Well, you've seen the complexity of the business. Hopefully, even for those of you that are working in something similar, you'll recognize that there is a lot of complexity in there. You've seen the complexity of the messages. There's such an amazing variety of messages. It covers up pretty much everything, and I didn't cover the binary because it's rather hard to just show on the screen. The nice thing is there's lots of customers out there and they've got lots of money. Some of them are losing it, some of it's all disappearing off in different places, but the nice thing is when they lose it, it goes somewhere else, and so all you've got to do is follow the money. There's a nice big list up here. We've got banks, hedge funds, broker-dealers, prime brokers, market makers, custodians, asset managers, asset services, clearing houses, electronic crossover networks, central banks, that would be the Fed, and things like this. No matter where the money is going, there's a big chunk of it going somewhere, and any one of these has to compete with the other ones. Even if they're in one country, they've got to compete with other countries. That's one of the big problems we have in the UK, is that the Europeans want to put tax on a lot of our banking networks, and of course that then makes London uncompetitive with Paris or Frankfurt, whereas at the moment 80 plus or 90% of most of the trades in Europe go through London. And even if it's the US competing with what may be China or India or South America or something, even if it's a federal side of things, there is constant competition in these things. The banks have to compete with each other. The money it's a global thing, so it's constantly going around. So there is constant pressure on here to move. So these are the drivers, and this is what's moving people forward. The nice thing is there's lots of them around, and as long as you can find the money, regardless of a recession. I've been in this business for nearly 30 years now. We've been through quite a few recessions and downturns and bits and pieces, and there's always somebody out there that's got some money to spend. You just need to go out and find them. There are other industries, for example, where when there's a recession they just disappear or they go out of business. And financial services, it's until money goes out of fashion, which may well happen, not hopefully in our lifetime, but at some point. There's plenty of business to be had. Give an example. This was one of the examples that kicked us off on this idea. So we've got multiple exchanges. This is a company which, should we say a bank, and again I'm anonymizing it here, who is effectively connecting to all of the different exchanges around the world, and they're providing a lot of information for their clients. The clients want to know what the price of a particular commodity, whether it be something as simple as rice or wheat or pork bellies, to something like a company which is maybe traded on multiple exchanges, to something like gold or even foreign exchange or futures, for example, or currency. What they're doing effectively is connecting to all these different exchanges, getting all the information in and effectively pooling it in what would essentially be called a dark pool. So it's an exchange which they can see, which they can now do best execution and find the best sums or deals to give to their clients. There's other opportunities here. If you see something that's quoted on one exchange at one price, a different exchange on the other price, then potentially you can do what's called an arbitrage, buy off one, sell on the other. It's typically done in sub or around millisecond time or sub-millisecond time, where you buy on one, sell on the other. Obviously, speed of light problems come in with this, but if the exchange one is in Tokyo and the other one is in Chicago, for example, everyone has the same speed of light problem. So if you can see a difference in price, if you're the first one there, you get the deals. Anyway, so this is what the client's trying to do. And this is the one that drove us initially. They were a Spring integration user. They were also a client of ours. And this is what sort of drove us towards picking up this architecture. It's very nicely split architecturally, as you would expect a design to be done. Effectively, they got feed readers that go off and read each of these feeds. They're nicely decoupled with a queue. In this case, they use RabbitMQ, but it could be any particular queue. This is an AMQP. And then they stick it into a large database. Now, in this particular case, it was Gemfire, but it doesn't really matter. It could have been Gemfire, Gigaspaces, MongoDB, could have even been Oracle. It could have been a flat file, for all we care. But the point here is we're dealing with the integration part, not the actual sort of end implementations. We sat down with a number of people. I know Adam is no longer at VMware, but they're all Spring committers. A lot of these names that you'll be very familiar with. We work as well with Mark Pollock and Mark Fisher, etc. But most of the raw code that was written initially was by these guys or with these guys. So let me show you how it works. So we took the Spring integration framework that you've got at the moment. Looking at it, it works beautifully well as long as you've got XML or Java. So we've got all these connectors on the bottom, so you can connect to a socket, to a web service, to a file or something, and it's very easy. You can read stuff off and you can process it through. You can take your XML and you can do XSLT transformations. You can do a lot with it. But go back and think just 10 minutes ago to some of the complexity that I was pointing out to you. How would we read those comma delimited files? That's fair enough. You go off and you create yourself a little tokenizer that puts them in, but then we've got validation on top of that. That's all very well. You've done one of them, but now our prime brokerage has 600 clients that send them through. And there's a turnover of clients. 10 of them disappear every month, and we sign up a new 20 every month. So you constantly got to keep doing these things. You don't want to have to employ a department of programmers to do this. Now, if you're looking for a job, that may be very well. You get a job, but you're going to get very bored of writing comma delimited file parsers after a while, and you're going to start looking for a solution. But of course, you're working for a bank, and there's no incentive to actually come up with a good solution because you're getting a salary and etc. That's the way it works. The contractor's dilemma: the faster you work, the quicker you finish your job, and the less you get paid. So effectively what we need to do is to add the ability to pick up all of these different message formats. So take on the fix, Swift, FPML, binaries, ACH, 20022, comma delimited files, ASN.1, all of these sort of weird formats. If we can come up with a standardized method or mechanism that does this, and hook this into Spring, we only need to do one integration, and that's the Spring integration, to use two words twice. And we used a tool called C24's integration objects to do that. And effectively what that allowed us to do was we modified the integration objects to effectively create the Spring bindings for us. So what happens is it has a lot of these standards already off the shelf, if you like. A lot of these other standards, comma delimited files, etc., you point it at one of these files, you import it, and you say, just like you would with Excel, this is a date field, this is a number field, etc., and here's the date format, here's the number format, here's how many decimal places it has. And then you can start to add rules to it, saying this date must be greater than this date. It knows it's a date, so it can do the maths behind it. Then you click on a button and it deploys the code for you. But because it can deploy the code, it's doing exactly the same as JAXB, JIBX, any of these other things. It's doing it not just for XML, but for these other standards. But because it's deploying the code, we thought, well, if we can get it to write the Spring configs as well, and we can now integrate this into Spring integration, effectively every time we deploy the code, we can now deploy a Spring config, and we can actually import this directly into Spring integration flow. And that's effectively what we did. So what this equates to is it's now the endpoint integration. So you've got all of the plumbing that you previously had. So you can still obviously read your XML files, you can read your Java, you can process it, but you can now add to it very, very quickly all of these nasty formats that we're finding in the banks. And there's very few formats within these financial services organizations that we can't now manage using this mechanism. Now, given the size of the complexity of this, it's not just as simple as, right, tick, 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 point at this one, do this one, etc. There's a lot behind it. You need to create metadata repositories, master data, and all this sort of thing, because when somebody talks about a currency or a trade leg, you want this common metaphor to be used right across. You saw all those boxes that I had. Each of those different parts of the bank behave very differently. The front office is all running around and everything must be done within seconds. The back office is, it's almost like insurance. It can take a week. Who cares? It's not quite that bad, but it's much slower. However, the values are much bigger. If somebody loses something in the back office, there's more than a panic. Everybody gets woken up out of bed, and people are sort of delving around inside the MQ series queues looking for the message that's got lost somewhere. So effectively with this, we can now hook up all of these different formats and standards with the idea of when we talk about a trade leg or a currency, that from the front, the middle, the back office, we're always talking about the same thing. So we try and create a metadata repository out of this. So a currency is always, or an amount is always a currency plus an amount. And there's ISO standards which look after that. So here's the process. Effectively, if we're looking to integrate something, what I'm going to do is go through just the process of this, and then I'm going to come and look at a number of different scenarios that we've actually put into production on these. So the process is relatively simple. Effectively, you're connecting up, we'll start with the simple A to B, or you're connecting A, B, C, D, E into, where do we get to, E, F. But each one of those you can treat individually. Now, there's two different ways of doing this. You can either use what we call a canonical format, so you can transform everything that you pick up into our standard, one standard format. We call that a canonical format. And you need to map everything into that, which is sort of good because it creates a standard format across the organization. Everybody can refer to that, and everybody knows how it works. The disadvantage is that everyone has to know how it works, and everyone has to understand it, and everyone has to download the libraries. It's not always that easy in the bank because in a very large organization, you've got literally thousands of programmers. Entire departments may have fired up a particular project 2 years ago, and they've got no programmers on it anymore. It's been running in production for 2 years. Why on earth should they keep the programmers? They move them on to a different department. So when you want to integrate to that system, all of a sudden they've got to go off and find the programmers. So it creates a dilemma as well. So there's two different ways of doing it. You can either transform it as and when you need it, or you can transform it into this canonical format. So if the format is known, it's going to be pretty much off the shelf. Also, within the bank, we could create off-the-shelf messages within the bank. There will be certain formats commonly used within the bank. There are also systems like Murex, for example, which probably half the banks use, internally, and then we can create common formats with that within the bank. If it's not known, it's what we call proprietary or a specific format. We can effectively, there's two ways. We could create a custom parser. We could actually write it completely from scratch. We could ignore this entire process and we could hook into Spring Integration. Or we could use what we've got with the tooling and effectively try and create a message format. The advantage it gives us is a common API that we can use right across the board for all the different message formats. So when we're importing this, effectively what happens is literally within a couple of seconds we generate all of the Java code. The Java code respects a common format. We've got a common API. We've got bean class methods. So we got, as you saw the Swift message before, we've got Swift mt564.getBlock3.get message type, for example. And we can start to use that. We've also got things like XPath. We've got the rules, so we can say mt564.validate, and we can validate the message. And that's very important. But it's a single validate method that validates, it works, it does a tree walk and works its way through the entire message. Imagine now with our flow, with the Spring Integration flow, we can hook up to a number of different message formats. We can bring them in, and without having to know what the message formats were, without having to understand how they work, we can simply say, validate yourself, validate yourself, validate yourself. We can walk through a queue and we can pick up messages off the queue and we can validate them because they all respect this same format, and that's really important. So as we read these in, this is using the XML config. We can read the messages in. Effectively, the source factory is generated. It generates a number of different source factories, have fixed sources, Swift sources, and of course you can generate your own, and we've had to do that in some cases when performance is an issue. Andrew, sitting down here in the blue t-shirt, will be talking immediately after this, and he's going to go into some of the more, he's from C24, so we'll be going into more of the sort of details of how they did the performance tuning between Spring Batch and Spring Integration. And these were some of the actual issues we had with some of the clients. Transformation. If you can understand the input model, so the input model is a comma delimited file, so it's nice and simple, it's flat. It's basically one file, many rows, each row has many columns. Not much to it. It's very unusual that you get any more structure than that. You can get more structure. You could have different sets of different types of rows. You have a header, of course, as well, optional header. But effectively, as you're processing this, you know the input format. If you know the output format, let's assume it's a nasty XML hierarchical format, you can now do a mapping from the input to the output. How do you do that? Well, there's a number of different mechanisms. You could use getters on the input and setters on the output, and you can say get this, set that. You can obviously say set, brackets, and then the get. Make it all in one line, and you now become a DS. Sorry? Oh. Okay. You now become, you know, a programmer that can now program everything in one line. You can now move on to Scala and closure and all these things. But you could also do it this way. You can do it graphically. Now you might think, oh God, another graphical interface. Well, yes, it is another graphical interface. Nice thing is that what this generates is Java. It knows the input, knows the output, it generates Java code. It literally generates, get this, use this function, and put the output into this. Get this one, add it to this function, add the other bit to this function, and set the output effectively. So it's generating the Java code. Now, if you're doing the nice, interesting work, the performance tuning, the multi-threaded work, etc., you don't particularly want to have to do this stuff. You want to get onto the sort of benchmarking, performance tuning, and bits and pieces. Leave this to the business analysts. Business analysts can't code, we know that, so you give them this, and then that keeps them happy. And then when it goes wrong, you can blame them that they got it wrong. So you need, in a large environment, you need lots of options. You need the coding options, you need the XML, just the same as Spring Integration, for example, or Spring, if you're adding annotations, you can do it in Java, you can do it in XML, etc. And that's the nice thing about it, it's flexible. So if we're moving on to validation, to kick off the validation, there's a number of mechanisms we can do that. We can kick off the validations. We can use header enrichment, so we can validate it, enrich the header to say, here's a list of problems with this message, and we can move on to treat it elsewhere, or we can throw it into a queue, knowing what the problems are, or we can actually say, this doesn't validate, and chuck it back immediately where it came from, which is generally one of the best ways of doing it. We can do XPath routing. So once we've got the message hierarchy, if we want to take any one of these messages, whether they be Swift, fix, FPML, comma, delimited, etc. We can use getters to get the information out. We can say message.get this, .get that, .get the other, but that's proprietary for each message. Each message has a different structure. We could use XPath. And if you're using some common metadata mechanism, you can perhaps use aliases, and you can just simply use / trade date, for example, and regardless of where the trade date is in the message, you can get the message out and you can route. So we can now say route trades over $100,000 this way, anything under go the other way, route trades that need to be processed today this way, trades that go the other way another day. This becomes very important now as we're designing this system. We can have multiple different formats on the input, and we can have a common workflow, if you like, that processes the messages regardless of the complexity on the input. So here's, we can do XPath Transformers, so we can basically kick off XPath. We can do routing through XPath. Now, because it's XPath, we can do routing not just on the content of a value, but the type of a value. This may not be immediately apparent, but if you've worked with XML, you'll know there's things like NEs and various different. It's a bit like having an abstract class. So it's like saying if it's an instance of this class, so I've got an object, it respects an interface, it's an abstract class, is it one of these or one of these or one of these? And we can do that sort of routing. So if we've got an FPML message, we can say if it's this type of trade, route it this way, if it's the other type of trade. So it becomes very powerful. And again, we don't need to know necessarily about the original type of message. So look at some of the client implementations. Now, these are going to be a couple of slides for each one. I'm extremely happy to go into more depth if anybody wants to know any more questions. So what we'll do at the end is maybe start up the questions and we'll go through them. I can always go back in the slides to refer back to them. These are all large banks. As I say, we've got at least 6 in production, and these are all using this combination of Spring integration. Being open source, of course, we have a number of clients. It's not just Spring. We've done these with the WebLogic, the WebSphere, all that horrible IBM stuff, Mule, all these bits and pieces. We've done transformations from IBM into Spring integration, for example. Some of them are combinations of Mule and Spring. There's a whole different set of tools we've used. Again, they're not just VMware products. We've done this with Gigaspaces. We've done this with Coherence. Neo4j, for example, we're messing around with it as well at the moment with some clients. So there's a lot of different scenarios that we've got. What I've got here is just 3 or 4 different scenarios, which I can go into a little bit more depth, but it's very hard for me to write them down without putting too much information that as the slides go out, the client goes, he's talking about our implementation here. And then I get into big trouble. Why do they choose Spring integration? Well, there's one instance here where we've gone and we've actually bought Spring integration with us because we were asked to go in and solve a business problem. So we bought the tool set with us. The vast majority of these, the client has already got the technology and we've gone in to solve the business problem using their technology. It's a bit like if you guys work as a consultant or a contractor, you don't go in and say, sorry, I'm not working on anything except IntelliJ. You tend to just have to go with what you're given. So they've got good access to, there's a good pool of developers. It hooks up nicely with the enterprise integration patterns. This makes it very nice for drawing out diagrams, etc. People tend to understand this. It's extensively well tested in the field. And there's also sort of this scenario of every bank's using it already. So unless we're doing it, if everyone else is using it, we pretty much we must be in the right sort of area. So it's reached that critical mass. Everyone's doing it now, so it's commonly accepted. If I was doing this talk, what are we now, 2012? If I was doing this talk 10, 12 years ago, I'd be talking about Java just being used in the banks now. It's now accepted. It's commonplace. It's all Java on Linux. We wouldn't even be considering Linux in a bank. We'd be running it on Unix. It was all Solaris in those days, AIX, Solaris, and HPUX. So these things are generally accepted. Spring is the de facto standard in the banks. It's more used than well, it's just the de facto standard everywhere you go at some point. good support, good documentation, plenty of community support and plenty of books. This is pretty much the reasons why they go with it. And then you've got multiple languages. So for those of you, myself included, sometimes you suddenly get a little bit bored of Java. You've got all these other languages that you can go and play with. And I heard some conversations back here about Griddle and Grails and all these bits and pieces. Everybody likes to play around with these. We have seen banks that have managed to get little tiny projects off in these different technologies, and we've introduced rules in Scala and Clojure now and Groovy. So it's a nice extendable language on this side. So go back to our Exchange integration scenario here. So effectively what they're doing, they've decoupled this. They're using a very, very lightweight reader. So they're basically hooking up to the exchanges. Most of the exchanges have a very specific engine that hooks up to the exchange. That throws out trades, typically on a TIBCO rendezvous or MQ series or something like that. They're picking these up, again, Spring integration, and they're popping them straight onto a RabbitMQ queue. They chose RabbitMQ, that was the one that they got, so it could be anything in this particular case. The interesting part of the sort of complexity, effectively, is on the right-hand side. Now, I put a box in there, and I did have a much more complicated box, and then I saw, again, comes back to the client will recognize this because all the bits and pieces I put in the box are all theirs, so they're going to sort of recognize it. So let me tell you a bit about it. So if the trades come in, effectively what they're doing is dequeuing off the MQ series queue. They're going to see whether that trade already exists, because you want the possibility of being able to replay trades through. So what you don't want, and this is the big thing that we try and avoid everywhere in all sort of, should we say, modern architectures, is transactions. You don't want the situation where you're holding these long transactions. Most of the trades that we do in a bank are what we call long transactions. They can be typically 1, 2, 3 days. So from something going in at the top and coming out at the bottom, in settlement could be anything up to 3 days. We have these new pushes towards what we call T+0, where we do same-day settlement. But even so, you're still talking about long transactions. Across multiple systems, you can imagine it would just grind to a halt. Transactions kill any system, large system, especially distributed. So what we're trying to do here is allow the same messages to be played twice. So if you push the same message in twice, 3 times, it's idempotent, actually nothing happens. And this allows you to replay things. If something goes wrong somewhere, you can just say replay the last batch, and off it goes through. So first of all, we've got to go to a cache. In this particular instance, they chose Gemfire. Again, could be any sort of cache in this case. So we go off, we check whether it exists in the cache. Come back, it doesn't, so we can create an instance of it. We then need to enrich it. So there's a lot of information that needs to be enriched. So we've got the trade off the exchange. We now need to enrich it and change some of the information that the exchange has referred to our information. The exchange may refer to a particular counterparty, that would be another bank, but we have a particular way of, or the client have a particular way of paying that bank, so they need to exchange the exchange's information with their information. So there's what we call enrichment and as such that goes on. And then finally, we need to decide what we're going to do with that trade and where we're going to route it. So we have routing rules in there as well. So some of the advantages in this and in using some of the caching technologies are obviously as we move into and this is obviously a very distributed environment, as we move into a distributed environment, we can now start to replicate some of these caches, the lookups for the routing tables, some of the enrichment data. We're not hitting databases for this, for example, so we've got all of this information stored locally, and this can now be fired off at a much, much higher rate. The sort of rates we're looking through that's on this are sort of in the high hundreds to low thousands per exchange per second. And we're looking at over 24 exchanges on this. So it's the sort of throughput that we're getting. We've had some interesting problems is not the right word, but we've had some interesting challenges, shall we say, with performance on this. They're not challenges that we know that we can do it, because every time that we've taken one of these challenges, we put enough manpower onto it, we partly re-engineer it, partly sort of recode some of it, and we can get significant performance increases out. So it's basically just you take something which is designed to be generic and you put it into some of the work that Andrew will be going through in the next talk. You take something which is generic and you put it into something which is time critical, and you start coming up against a few bottlenecks. So it's been interesting, but it is in production. I think that's the one I just talked through. Yep, it is. Another one. This is post-trade capture reconciliation. This is again another very large bank, and effectively they have existing integration technology. Every bank has pretty much every integration technology you can possibly imagine. Virtually every vendor will claim they're at one particular bank. Obviously, vendors would never lie. They're obviously in all these things. These banks are so large. We could sell, or we have sold, for example, to some of the larger banks, the cities, the JPMCs, etc. And you could sell to them 5 times over without any of them knowing about any of the other implementations. Also in the same country. It's quite possible, and you can actually introduce people from their own bank to each other people and to other people within the bank. It's quite strange. So this is a very large client, and effectively they've got an existing legacy in integration system. And so what I've done is to highlight some of the sort of areas. It's fictitious. I just picked out a few of them, but to give you an idea of it's sort of just at the edge of the front office, through the middle office, pushing into the back office. And what this is doing is basically preparing number of different trades, picking them up in comma delimited file formats, picking them up in FPML formats. There's no Swift from recollection in here, and effectively pushing these through the bank system. And it's this is the one where we've working with the Spring guys, we got the client we've got a lot of different parts that we're working on this. So what happens in Spring integration, as some of you who've worked with it may have noticed, when you get the XML configs, they get horrendously complex. And then you start adding the exception handling as well, and you end up with this XML config that is just horrendous, and you find yourself constantly doing finds and things to find out what you're looking for. It gets very confusing. You then create some test scenarios, you then do cut and paste, and then you start basically sort of commenting out some of the XML, and it just gets more and more and more complex and very difficult to manage. So what we introduced them to here was some of the work that Oleg had been working on with the Scala DSL. So effectively what the Scala DSL does is it takes aspects from the XML, creates a Scala variable around that, and it overloads the -- greater than to look like an arrow. Do you have any examples in your? I don't. You don't. Okay, it's pretty neat, and effectively Oleg was developing this at the time, and we thought this would be a superb case. We've been using it, we've been playing with it, and this would be a superb case to actually demonstrate to the clients how much simpler it was in this particular case to take an otherwise 5 to 6 pages of XML config and produce 3 or 4 lines of Scala DSL. Now obviously behind the Scala DSL there's the implementations, but it's still, for the configuration, it becomes beautifully easy to understand. In the process of this, we had quite a team in this bank, and we actually implemented, obviously with the help of the Spring guys, all of the JDBC and JPA implementations on the Scala DSL. So this is now sitting in production. So this is one of the few fully productionized versions of the Scala DSL on top of Spring integration that's gone into a large bank, and this has been running for quite some time now. So it's a superb example of how moving into some of these DSL languages, this could have equally well been done in Groovy. In this particular case, we just had a good relationship with Oleg, and it just seemed the perfect one to use. So it's a language which is, Scala itself is sort of reasonably well defined, but it's something which I find is quite interesting, because if you were to use this now and you have some ideas, for example, it's not that revolutionary to want to connect something to a database, but if you were to be working on this now, you're in a stage where you can actually start to commit back to this, and you can start to define this DSL yourself. So if you're interested in this sort of thing, it's something that you can actively work with. Once you start using it, you'll find little tweaks and little bits and pieces. It's beautifully simple to run once you get kicked off with it. This was another example of a hedge fund. It's actually a hedge fund within a bank. Banks have their own internal hedge funds. And the hedge fund, effectively, hedge funds have lots of clients. Their clients are large organizations, companies, etc. And these companies need to do their own payments, need to process their own finances, etc. And typically they send these to the hedge funds, and the hedge funds do them for them, but the hedge fund could then send it off to a prime broker, etc. But the prime broker costs money, therefore the hedge fund would want to do it themselves. Everybody's trying to save money, which is good because they spend the interim on the programmers and architects and other companies, SIs and what have you, and we all make money out of it. You see where I'm going with this. I'm trying to show you how to relieve the banks of all of their money. It should go from banks to IT people. That's my belief. And then we reinvest it back into the banks. And then we pull it back out again. So this was a hedge fund. The hedge fund, effectively, it's quite simple, just wanted to be able to provide multiple interfaces and APIs for their clients to use. And there's not really much to go into in detail on this. Effectively, it's providing access from internal systems to external systems. And so wrapping those with APIs, REST-based APIs, validation, these sorts of things. So the messages were piped in, we could validate the messages. We defined all these flows using Spring MVC, Spring integration on the back end, and of course all of the sort of scenarios that I've talked to you about before. Another interesting scenario was a matching engine. Now, over the numbers of years, let me tell you what a matching engine is. If you're a bank, a trader or something, and you agree to swap some money with someone else, or you agree to do a trade, it's always with someone else. You're buying something that they're selling, or vice versa. So part of the way through the system, you need to agree that what you decided to buy is what they decided to sell, and vice versa. So you have these, they send, here's my understanding, and here's my understanding, and both sides effectively match. But also with most trades, there's two parts of the trade. There's the buy and the sell. You're buying something, you're receiving something, and you're giving something out. So even if you're doing an e-commerce thing, even with eBay, you're sending money out and they're sending the goods in, and you have this confirmation system where you say excellent sender, excellent buyer, excellent seller, etc. And that's effectively the confirmation. So in the banks it's exactly the same, but it's a little bit more complicated, as you might imagine. If you're buying currencies, you might be buying one currency, borrowing one currency for 2 years and then paying back in small amounts every 3 months, for example. And so what you need to agree is the amount that's been sent in one way and the numerous amounts that have been sent the other day, plus all of the dates that those amounts have been sent and to who they've been sent throughout the system. So both banks have matching engines, and they match, is my bit the same as your bit, and is my understanding the same as yours. And also internally in the bank, trades get separated off in different parts, and is this the same as that? If something's been paid, sometimes the payment routing will go off in a different mechanism because it's going through a different currency, and when it comes back you need to match it. There's also the concept of reconciliation. Reconciliation is when you've got multiple things and you need to effectively work out that they're the same. So if you're buying trades, you might send an instruction to buy 10,000 trades. Someone else may sell you 10 lots of 1,000 trades, and you need to make sure that they reconcile together. So in every bank there are literally dozens and dozens of matching systems and reconciliation systems. And there are businesses which survive solely on selling just matching engines and just reconciliation engines. One of the issues, you might think, well, hang on, if they're buying one matching engine, why don't they use it for everything? It's a bit like caching. You could say there's a caching solution. You could, a hash map is a caching solution, but it doesn't solve all of your caching problems because we end up with big data being one. But then you wouldn't go off and use Cassandra just to store 100 values that need to be looked up on a hash map, for example. So there are different solutions for different things. So we've gone out to create these matching engines where there may be only a few hundred trades a day going through these systems, but at the end of the day they can't do it on Microsoft Access. They can't do it on an Excel spreadsheet. Someone has to go and write the programming. And somebody ultimately has to integrate to these systems to actually read the trades and read the information out of the trades to do the matching. So effectively, a matching engine takes two feeds, and there's one output that just says yes or no. Of course, there's a little bit more complexity to that as you get bigger. You want to go back in and see what matched, why it matched. Then you have proposed matches and forced matches, forced break matches, and all sorts of other sort of weirdities in there. But keeping the simplistic side of it, it's basically two inputs where you hold all the values for a while, and then you basically just say yes, match, no, etc. So, in particular, the first one we used was MongoDB. Why MongoDB? Well, we had to do two things. One was a foreign exchange system. Next one was derivatives. Now, foreign exchange is relatively simple. It's a price, an exchange rate, and a date, and that's about it. But when you get onto derivatives, there's a lot more complexity to them, and the complexity is not flat enough to. They can be stored in relational databases, but the derivative changes every few weeks because somebody keeps changing the standard, or somebody suddenly decides they want to add something new to it. And you end up with your schema changing constantly, and it just gets more and more and more messy. And then you end up with all this object relational mapping crap, which is about the biggest slowdown of any system after transactions. So add transactions and ORM to your system, forget it. So if we can get rid of the object relational mapping, we can get, obviously we've talked about the transactions, effectively we can bung this into a MongoDB, and in this case it could be MongoDB, it could be any one of the Neo4j, Cassandra or something like that, any one of these. It doesn't particularly matter for what we're talking about here. So these trades go into the system, and all we now need to do is effectively make queries based on whatever we're looking to match. And what we tend to do is we look for the how distinct the values are. So if we're looking for dates, we don't have a huge amount of dates, so dates are not a good field to look up. Trade ID generally is unique. So if we can look up trade ID, we can index those and we get a much, much better hit. Once we get the trade ID out, as an example, sometimes we have different trade IDs, so it doesn't work. So we try and find something which is relatively unique. So we do distinctness tests on the data to work out how distinct the data is, to work out what the probability of hitting the right trade is. And we can run these through quite regularly. So as we bring out the trades, the idea is if it's very distinct, we found the right one immediately. If it's not very distinct, we find a group of 10 of them, and then we programmatically do a walk through them and work out which one of those match. Sometimes you can't match them immediately because you have what's called tolerance matching. So we may say $100,000 is acceptable if it's $99,950 or $100,050. So we have a $50 sort of match. Also, if that's in a different currency, we could still say it's $50, but $50 in the local currency. So then you have to do a transformation on the amounts to check it. So there are little complexities that go in there. So effectively, all of these trades go into the MongoDB database. We have a little engine that constantly works out every day or so how distinct the values are. And as we want to match those back, we bring them back. That brings it down to sort of typically 1 to 3, 1 to 10. And then through the 3 or the 10 that we have left, we then work through and do the tolerance matches, and then we kick out the results on the outside. So it's getting a little tiny bit more detail, and again, will be a lot more code later. Connecting to MongoDB in this particular case is beautifully simple. Equally so with a lot of the in-memory databases. I say database in-memory cache. Cache is the wrong word for a lot of these things, so call it an in-memory database as well. This is the loop. Now, it's not particularly well color-coded, so ignore the top. That's obviously just initializing the variables. And this, of course, is not production stuff. This is just a prototype. So if we go just past the try here, effectively we're getting the file, opening up a file. Now, the file has a list of values in it. Now, the files could be a socket. It could be something else. Imagine these have arrived now as a batch. So as we go through these, we open up a file reader, a buffered file reader, and then sitting in the while, what we're basically doing is we got this template class. Now the template is effectively just as you can see from the initialization, it's the original message and then a possible list of errors. Now what happens is we pass in the original message, it gets parsed in a parser. We can multi-thread this sitting in the background. The parser takes the original binary or byte array message, puts it into a structured bound Java object, and that effectively is then put into our MongoDB. So we see at the bottom MongoDB template, or the Mongo template, save, and we're basically just saving the bound Java object into the collection name. And of course, on top of that, we can enrich that with automatic indices, indexing, etc., and then do the queries on top of that. So the matching, the advantage we have now is we have a very generic matching engine which we can feed numerous different formats into it. So we can feed formats from fix, FPML, comma-delimited file formats, but the engine, the matching engine itself remains unchanged. So it's a constant, it's an engine that we don't need to modify for the different types of trades. Now, that's my last slide. I just want to introduce Andrew, who will be up here next in another half an hour or more. Yep. Andrew will be going through a lot more detail on the performance tuning that we've been doing on this. I think if you're interested in the technology, you'll probably find that interesting. From my point of view, I'll open up to any questions. Nothing at all? There we go.
What is the way how you manage that all the different type of fixed formats and serve the same way? Is that, how is that?
Sorry, you're going to need to speak a little bit louder, then I'll repeat the question for you.
What is the canonical format? I think that's the question, right? Yeah. What is that canonical format? How do you handle all those different formats the same way in your Mongo database?
Okay, so what are the canonical formats? Typically in a bank, it's very hard because the front, middle, and back office have three very different parts or parts of a bank. And then on top of that, from what you saw with the green part, it's often designed into silos. So you've got fixed income, derivatives, equities, etc. And they're all different parts, and they have different vocabularies between them. So the canonical formats that we typically find, FPML is probably the one that covers most of it, but the design that has superseded FPML is ISO 20022, which has a part of incorporating most of the trades that we go through this. Now, in the example that I gave for the company that was doing the hooking up to all the different exchanges, they chose a fix 5.0 because they didn't have any middle and back office, effectively. There would be very little point in having canonical formats like FPML or Swift, which had lots of information about stuff that they don't need. So their canonical format was actually fix. So they normalize all of their external formats into fix 5.0. So there's a number of different banks that use different formats. So I suppose the most common is probably FPML because it's the most encompassing format, which is why we have so many different standards of it, because each of the banks and hedge funds use it, and then they, a bit like Spring, I suppose, they modify it themselves and then they commit back to it, and there's a committee and that gets moved onwards.
Basically, you are choosing the most complicated, most the biggest format.
Yeah, so
How do you get to that? That's just being my question. Who's going to do the transformation? Is there some way?
yeah, so the question is, do we choose the biggest, most complex format? Sadly, yes. That's one of the arguments. It gets very hard. So you can show this sort of, here's my integration problem. I've got 10 things all integrating with each other. Then it's sort of 10 factorial possible different combinations of how I'm going to connect up with this. Or we can say we'll introduce a canonical format, and we basically got 10 different transformations from the 10 different things into this canonical format. However, they all argue that, in fact, they don't need to connect to 10 others, they need to connect to one other, and that system has been working for the last 10 years, so why should they now take this? They go from their 20-line common delimited format to a 3,500 field XML format, and it becomes a big headache. So how do they do it? Sometimes we try and avoid the canonical format, and we work on a metadata format. So this is why ISO 20022 is becoming a little bit more popular than FPML. FPML dictates a single message. 20022 dictates a vocabulary. and you use the bits of the vocabulary that you need, and you make up a message on using that vocabulary. Now, if you understand the vocabulary because it's an ontology that you understand, you can work out what's in the messages. So you don't need to transform all of those bits. What we use for the transformations, if the bank has lots of programmers, and most of the transformation needs to be done at a low level, then we suggest getters and setters. It's by far the fastest way of doing it. If the bank has lots of business analysts, and the business analysts were the people who described or spec'd out the transformation, most of these messages have a lot of business information in them that goes well beyond the average knowledge of even the most advanced investment banking programmer. So you'll end up with sort of fields that people will look at, and they'll look at 3 or 4 times and think, I've no idea what that means. And they'll have to physically go and find someone that understands it. So you tend to leave it to the business analysts, and that's where the GUI comes in, and you leave the business analyst to do the dragging and dropping. Now, the result of that is never as performant as the straight transformation. The other problem is it's a bit like giving business analysts Excel. Excel is the nightmare of virtually every bank. It's the only reason Microsoft is still in the banks at the desktops, because of Excel, because everything's done on Excel. But it's a nightmare to manage, and everybody writes their macros and things in different ways and uses it in different ways. And the same is true if you present them with a GUI. They come up with different implementations each time. So you can try to give them tooling in such a way that you can create functional graphical maps. So you can now group common transforms into a function, and you can then reuse that function. But unfortunately, you've then got to make sure that you train all of the business analysts and keep them all trained up all of the time. And this is why it's never quite as simple as as I would love to be able to just point out, because you do have horrendously complex messages, and it's never quite as simple as you might think. So it does create a headache. So if you have a headache, I'm just acknowledging that it's not unnormal. It's like if you drink too much one night, you're going to have a headache in the morning. It's
So can you talk a little bit about the strategy you used about not replaying, essentially not being able to replay messages and dropping messages that you'd seen before? Talk about a cache. Are you looking at the entire data set of the entire history of all messages?
No, typically what we tend to divide messages, typically it's always a compromise. So just to repeat the question, asking about the strategy used for sort of replaying messages, it tends to be a compromise on how important the messages are to you and how long it takes to reload things. Now, if you lost a machine, for example, and then had to reload it, but it took half an hour to reload, and then you've got all your business data going on in the background, it becomes a headache. If you can take small enough samples where you can effectively give you one scenario where sort of every hour we take snapshots, and then if we want to play something through, we can choose the hour that we want to do it. So we can do the last hour and a half, and we play it through in chunks of hours. That works particularly well in that scenario. What's important is that if we play, there are complexities because messages need to be played in order. So you get buy, sell, or you get a buy, cancel, buy, sell. So buy, if the buy is wrong, you'll cancel the previous one. You'll create a new one with a new number, but with the same trade ID, and then you'll do something else further down. So you end up with even numbers and odd numbers. So the odd numbers are the cancellations. So you end up with all these things are sensitive in the order that they arrive. So you need to be very careful about the order that they arrive in, and you need to be careful that if you play back a particular hour that you don't get out of sequence because the previous message was in part of the previous hour. So typically they'll be holding an entire 24 hours. It's quite easy in financial services to cut off on a 24-hour period. And most of those can be sort of matured into a sort of different category once they've gone past the 24 hours. Most trades are completed during the day. If they're not completed externally, they're completed and moved on internally. So what we ideally need to be able to do is if something's gone wrong or something's gone missing or we need to replay through something is the ability to replay those trades through. Some of the scenarios, problems that we've been having are using some of these caches, for example, in-memory caches, is that we're not expiring the in-memory cache, and the in-memory cache is now getting full because whether we be in production, pre-production, in some cases they tend to merge the two because you can create multiple caches within within the same cache. And so we've had scenarios where things have started getting full up, or we've got replication going on and the replication is getting killed because people are running stuff through numerous times. So it's a careful balance between what we need out of it, but the key there is just not to use transactions, not to say start transaction, process the message, end transaction. Your system just dies. I mean, every system I've gone in there, I've never seen anything get past 10 messages a second, and I can take things up way beyond that, into the thousands per second without transactions. It's much easier to do compensational transactions to say, I processed 15,000 messages in the last minute. Did I get all 15,000 out? And was the checksum of what I sent in the same as what I sent out? Yes, good, fine, it's done. No, it wasn't. Send them through again. It's much easier to work on that basis.
One follow-up question on that, actually, if you are seeing that you have sometimes long running, like 3 days transaction or something, which obviously don't want to do an exit transaction or some type of long running transaction, why don't you rely on Spring Batch, on bringing it up to steps, and then still relying on exit transactions to make sure that nothing is actually possible to be lost, that you actually divide your large transaction into smaller? Why?
Okay, so the question is why are we not dividing this into running it through Spring Batch? In many cases we are, and Andrew's going to go into that in quite a bit more detail. If we get a batch, generally speaking, it's much more efficient to process it as a batch, particularly if they're sequence dependent, because there's no great advantage. You can't parallelize them if they're sequence dependent. You can parallelize the processing of them, but you've still got to have something which basically puts them back into order when you get back out the other end. So yes, we do use batch. We do batch processing. Batch processing is an optimization, shall I say, rather than a. I mean, it's sort of processing real time in chunks, but we do definitely use batch. So there was another question. So the question was, I made reference to Mule, and then you're asking the different points between the two? It's a little unfair to sit in a conference in Spring Integration and give you positive points on a competitor, but it is open source, so, but both companies make money out of it. It's hard to say one over the other, to be honest. There are some. I mean, I use both all the time. It's like, I'm using a Mac, as you can see. Do I use the Apple's Java or what is it, Oracle's Java now? It's most of the time it's the client that decides. The client is a large bank, and they've already decided some long time back that they're going to use a particular technology. If we walk in to a brand new client and they want something relatively simple, then it's a bit like the question of how do we do the transformations? Do we use getters and setters, or do we use a graphical transformation? The question depends on the people that are within the bank and the sort of culture that the bank has. So the question, again, whether we use Spring or Mule would come down to partly the culture of the bank. If they're avid Spring users and everybody's trained up in Spring, then it would be, I mean, Mule uses Spring as well, so there's no reason why I wouldn't want to do that. I think the UI on Mule is far superior than what you get on Spring Integration. But other than that, I think it's more down to the culture. I mean, I would be uncomfortable giving you a list of pros and cons on both in a conference which is designed to be Spring Integration. Catch me at the bar and I'll go into a bit more detail.
One question on these things about security. You probably ran into that many times. So what is the way you secure all these integration channels and things like this? How do you secure?
So, and was the question around security?
Yeah.
It's quite easy. There's an easy answer for that. Banks work on physical security. So it's It's a wonderful, simple answer. Banks effectively have physical security. So there is no connection between what's inside the bank and what's outside the bank. We're not working in an e-commerce environment where somebody can hack through one or two firewalls to get into it. The biggest threat is from somebody inside the bank doing some rogue trading, as you've well seen from past examples. There's very, very little threat from code running inside. So the biggest challenge is making sure your code is tested, not the security within the bank. There are Chinese walls within certain parts, but again, that's physical. So the systems have no physical connection between each other. So it's not something that there are issues with which users can access it, but again, it tends to be more. There's the developers and then there's the users. The users tend to be they're traders, so everyone on the trade floor has access to everything.
Yeah, the reason I'm asking is because sometimes actually right now in our company there are some connections which we are quite parallel, even internal connections to the servers like web services or whatever GM connections to the entity, just to make sure that because you have to comply with all these regulations and then so the same thing is probably coming up.
Well, there's there's PCI regulations where, for example, you have to have signing in books. It's only certain named people are allowed in the server rooms, and they have to be named and authorized, etc. And you have to sign in and out when you go in and out. But the stuff effectively you deploy. There is no physical connection between the test environment and the production environment. I could run all sorts of, there have been cases, if I go back 15, 20 years, where I could write something on a network and I could completely take down the production system.
Actually, it's not like that. I know one company they actually had their UAT environment turned into production, like switch, and it actually caused problems, but it's not exactly.
Well, Visa mandate the PCI regulations, and I'd be surprised if they get through their PCI regulations if they they have that sort of scenario. It's pretty strict, as you know.
Good lawyers there. So.
Good lawyers, yeah.
There's also, John, the wiring encryption to the parsing.
Yeah, there are other. As Andrew pointed out, there are things. For example, again, Visa's one of our largest clients, and there's a couple of things there. If they have these, I call it obsession, but it's quite natural. They go through and they check your machines for any sets of 16-digit numbers. So if you end up putting an extension after a phone number, you'll get had up for having a Visa number in your machine. For example, you can't put USB. You put a USB inside one of their machines, the doors get locked, and you end up with security descending on you very fast. So there are lots of things like that, but there are other things, for example, in the code that we had here, where you can encrypt an individual field at the field level. So we can have we can change the parsers and formatters. We can take the formatter and we can actually code it in such a way that you can never actually write something out. So it never physically gets written to disk, for example, and we can actually put encryption at the field level. So if there are things that need to be encrypted, it's some help, shall we say. There's a question next to you there.
Yeah, I'm sorry, I'm working on the same project, but there should be no problem though if we have to have encrypted channels with backing a channel with an encrypted.
Oh, not at all. No. No, a channel. An SSL channel. Yes. Something like Visa, which has, for example, connectivity. We were working on V.me, so which has connectivity to the outside world. Then yes, there's a huge amount of encryption and unbelievable levels of multiple changes of format through different firewalls and all sorts of stuff. It was yeah, these are all Spring plug and play. So you just put an encryption channel in there.
Ours is completely internal, but yet we still have to encrypt everything.
Can I just say while my audience disappear, thank you very much. And if there's any other questions, please come and grab me.